are studying viscosity. Viscosity. Viscosity is a fluid friction. Simple definition, that is, it is a friction in fluids. Here in this viscosity we are going to study the relative motion between different layers of fluid experiences a dragging force. That force is called as viscous drag. Viscous drag. In liquids, here this viscous drag is due to the short range molecular cohesive forces, and in gases it is due to the collision between fast moving molecules. That means this viscosity property is both in liquids and gases, but difference is that in liquids, in case of liquids, this is due to the short range molecular cohesive forces, and in gases it is due to the collision between fast moving electrons. Now here suppose we consider a diagram. Suppose liquid or fluid flows, then here suppose this is the uppermost layer, suppose this is the lower, again this is the lower. These are the different layers whenever liquid flows. And here we consider suppose last layer. And this layer is stationary layer, which is in contact with the surface. And as we go in upward direction, then velocity of the layers goes on increasing. Suppose we consider, suppose a layer which is at distance x from stationary layer, and suppose its velocity is v. Then from this layer, suppose you consider upper layer which is at a distance of dx, then its velocity is v plus dv. And we consider another layer from this layer again which is at a distance of dx, below that layer, then its velocity is v minus dv. Then we will define here what is meant by velocity gradient. Velocity gradient, we have to define this velocity gradient. Here velocity gradient means it is the rate of change of velocity with distance measured from a stationary layer. Suppose you consider dx is the distance and dv be the change in velocity, then velocity gradient we simply defined, that is velocity gradient is equal to dv by dx. It is the rate of change of velocity with respect to distance. Now we will see next one, that is Newton's law of viscosity. Newton's law of viscosity. First we will see statement of this law. Statement. Here we consider for a streamline flow. First thing, that is flow must be streamline flow. For a streamline flow, viscous force F, so we consider here viscous force F acting on any layer is directly proportional to area A of the layer and velocity gradient. Velocity gradient we consider dv by dx. That means we repeat again, that is for a streamline flow, viscous force F acting on any layer is directly proportional to area A of the layer and the velocity gradient dv by dx. Therefore, I will write mathematically here, that is F proportional to A into dv by dx. This is the mathematical statement of Newton's law of viscosity. Now we will simplify. Therefore, we write F is equal to eta A into dv by dx, where this eta is called as constant of proportionality, or we consider here eta is coefficient of viscosity. Eta is coefficient of viscosity, and therefore we write here eta is equal to F upon A into dv by dx. This is the mathematical definition of coefficient of viscosity. Now, how will we will define this coefficient of viscosity? Coefficient of viscosity is viscous force per unit velocity gradient per unit area. Or we can write here coefficient of viscosity is viscous force per unit area per unit velocity gradient. And SI unit of this coefficient of viscosity is, from this formula we will write unit of eta here, that is unit of force is Newton, then Newton second per meter square, or CGS unit we write dyne second per cm square, and it is also called as poise. That means here you see, suppose we write here units, unit of force is Newton, unit of area is meter square, unit of velocity I will write here meter per second, and again here 1 meter. These two cancels, this s goes upwards, therefore Newton second per meter square we have written here Newton second per meter square, and in also CGS system we write dyne second per cm square, or we call it as a poise. I will repeat again. Here see Newton's law of viscosity, that is for a streamline flow, viscous force F acting on any layer is directly proportional to area A of the layer and the velocity gradient dv by dx, that is F proportional to A into dv by dx. Therefore, F is equal to eta A into dv by dx, where eta is called as coefficient of viscosity, it is the constant here, and therefore eta is equal to F upon A into dv by dx. And by using this formula, we will calculate the unit. Here you see, unit of force is Newton, unit of area is meter square, velocity meter per second, and this dx here, mm gets cancelled, this s goes upwards, therefore Newton second per meter square, and therefore write unit of eta in MK system or SI system Newton second per meter square, or in CJ system dyne second per cm square, and it is also called as poise. Now we will see next article. Stokes law. Stokes law. Suppose we consider, suppose this is the tube containing liquid. Suppose we consider this is the hole is the liquid here. In this tube, suppose, or in any vessel or in any container, suppose this is, it contains a liquid, and suppose here a small sphere falling through a viscous medium. Suppose this is the small sphere. Suppose this is the small sphere. Now it is falling in downward direction. Then viscous force, see here, viscous force F. We'll see the statement of Stokes law. Acting on viscous force F acting on a small sphere falling through a viscous medium is directly proportional to the radius of the sphere, directly proportional to radius of sphere R. Then secondly, directly proportional to its velocity V through a fluid, and third one, directly proportional to coefficient of viscosity eta of the fluid. That means I will repeat again. Viscous force F acting on a small sphere falling through a viscous medium is directly proportional to the radius of the sphere R, its velocity V, its coefficient of viscosity eta of the fluid. Therefore, I will write here Fv coefficient of that is force due to viscosity Fv proportional to eta Rv. Here, to remove this proportional sign, we will take the constant. Therefore, Fv is equal to 6 pi eta Rv. This 6 pi is constant of proportionality. This is all about the Stokes law. Now we will consider next. So I consider the same diagram here. Liquid in the vessel and ball is falling. Then we will see terminal velocity. Suppose a sphere is falling through the viscous liquid. Then here the forces, different forces on the sphere are, that is, first we will consider, I will write here, first force, that is viscous force. I will write by Fv, which is directed in upward direction. Fv is directed in upward direction. Then second, that is its weight Fg in downward direction. And third one, buoyant force, B-U-O-Y-A-N-T, buoyant force, we write it denoted by Fb in upward direction. This force is in upward direction. That means I will show here. Suppose weight mg, Fg in downward direction, then viscous force Fv in upward direction, and also another force Fb is also in the upward direction. Now we will consider R, radius of object. R is radius of object. M, mass of object. Rho, that is density of object. Sigma, density of viscous fluid, and eta, coefficient of viscosity. Now here we write total downward force is equal to total upward force. Total downward force, I will write here Fg is equal to viscous force Fv plus buoyant force Fb, and therefore I will write here mg is equal to viscous force plus buoyant force. Viscous force plus buoyant force. Now here mg I will write, suppose 4/3 pi r cube, this is the volume, then we multiply by density rho, this is the mass, into g, this is the weight. 4/3 pi r cube rho g is equal to viscous force 6 pi eta rv plus buoyant force we consider 4/3 pi r cube into sigma into g. This buoyant force is due to the liquid. That means whenever the sphere falls down, then same amount of liquid is displaced anywhere, and therefore we consider same volume of liquid. 4/3 pi r cube, same volume as that of the sphere, but here we consider sigma, that is density of liquid, into g. Now here we write therefore 6 pi eta rv is equal to, suppose 4/3 pi r cube, and this rho minus sigma into g, and therefore v is equal to, after simplification we get here 2 by 9, then r square small g into rho minus sigma upon eta. Suppose we consider here this is equation number 1, this is equation number 2, and this equation number 2 gives the constant velocity of the sphere. We call it as a terminal velocity, or we can write here, or in terms of eta, we write eta is equal to, only v here and eta there, we write here 2 by 9 r square small g rho minus sigma upon v. This equation 3 gives the coefficient of viscosity. Equation 2 gives the terminal velocity, and equation 3 gives the coefficient of viscosity. This is all about the terminal velocity. I hope you all understand this. Thank you.